Taiwan 5-6 years ago, so it's good to have you back again. He did his PhD in Ben-Gurion University, and did his postdoc in Los Alamos and San Diego, and now back to Ben-Gurion. Although he's with the Department of Chemistry, by training he's actually a physicist for sure. But he's going to tell us something about molecular junctions. Let's welcome Yoni.
So thank you very much. Thank you, Chite, for this fantastic opportunity to visit Taiwan, which is a great place. If you take a picture, you have to send me a copy.
Oh yes, I will, yes.
And all the money that we make from YouTube, I want it. Millions of hits.
Yes.
Yeah, probably not. Okay. That's pretty much it. So, yes. So I'm at the Department of Chemistry at Ben-Gurion University of the Negev. And I'm at the Department of Chemistry because what I've been doing in the last 3 or 4 years really is at the intersection of physics and chemistry. But as Chite correctly pointed out, I'm a physicist by training. So what physicists do is try to take very, very complicated systems and try to make very, very simple models out of them. And this is kind of the spirit that will be behind all the things that you will see here. So this really is a physicist's way of doing things. These are pictures from my campus. It's a beautiful campus. It's just an hour from Tel Aviv. So if any one of you is in Israel, is more than welcome to visit us. And this is half an hour drive to the south of my campus. You get to the high desert of Israel, where there's literally no rain at all. People from Asia, it's hard for them to believe that such places exist. But there's no rain here. You see on this barren landscape, it's really quite beautiful. And I want to tell you stories that come from my collaboration with Professor Ben-Gurion. He's now at the College of Engineering at the University of Georgia. So if this is a map of Israel, by the way, this is roughly also the length of Taiwan, about 500 kilometers, roughly speaking. So all the universities in Israel are here. And this is Beersheba, it's the southernmost university. So this is technical, this is about an hour drive. And so we are the southernmost university. And Professor Ben-Gurion is at Georgia, which is in the southern part of the US. And since I'm telling 3 stories about molecular junctions, so that's 3 tales from the south. And let me first give you a brief introduction, and let me first start by asking if there's something that I'm saying which is not clear, or if there are any questions, please go ahead and ask me. You see, I'm not a very formal person, so I don't care if you interrupt me in the middle. Just ask if something is misunderstood, and I will answer it gladly. And molecular electronics, really, is quite an old idea. It came up, they originated in the paper by Aviram and Ratner in 1974, where they suggested you can use molecules to make diodes. And this was the original idea. And when you think about, I think they were maybe motivated by a much earlier publication. And what a molecular junction really is if you zoom in on this part, what you really see is a tiny molecule here sitting between these bulk electrodes. So really when you think about single molecule electronics, you're really thinking about taking a metal wire, making it, prolonging it into a very long, and now metals, they do not break, they just become thinner and thinner. Eventually when they do break, the apex is about 10 atoms. It's really, really small. And if you can put a molecule inside, you're going to force all your current through that molecule. Now the idea is that to make molecule technologies that will complement and eventually supersede present-day microelectronics. And the reason is twofold. One, molecules are very, very, very small, right? The size of the device, if you can make a device, the size of the entire device will be of the orders of a few nanometers, right? Now, if you go to the semiconductor, to the processors and the transistors that Intel are making, sure, the trench is 12 nanometers in size, but the device itself, the entire single PN junction, is probably 500 nanometers. So these are fairly large devices. If you can make a device where the whole thing is 5 nanometers or 10 nanometers, then you can increase the density of processors per chip by easily 10 to the 5th. So this is one idea. The other idea is that molecules, first of all, they're very cheap, because carbon is even cheaper than silicon. And the second is that the variety of molecules is essentially infinite. Just tell the chemists what you want, and they will produce it. They're really good at it. And they've been doing it for a very, very long time. So there's really a lot of room to play with, and this is kind of the goal of molecular technologies. And in recent years, I'm just giving an overview to my other talks, but in recent years, people have been going beyond electronics into other functionalities. Some example are Opto-Electronics, which I will mention here. This is the idea of making devices where you couple to the electronic system using light. Spintronics, where you couple to the spin degrees of the electrons inside your molecular junction. And of course, phononics, which is the manipulation of the vibrations inside your system. And these are all very active fields of research, and you can really read about them in these actually two quite recent reviews. They're very, very readable, so it's really nice. And I've been doing quite a lot of these things for quite some time now. And in my group, we've studied various systems, which I will not tell you about, and molecular thermoelectrics, which is a big thing to me. I've been doing it for a long time. And this is the idea of converting temperature gradients into power, electrical power, using molecular junctions, molecular photovoltaics, which may have various benefits over semiconducting solar cells, and molecular phononics. This is more of a theoretical playground for us, just taking simple systems and playing around and see what you can do. But what I want to tell you about today, the three tales that I want to tell you about, really have to do with the question, can you mimic microelectronic components with single molecules? And I will give three examples. The answer is, of course, yes, otherwise I wouldn't be talking here. And I will give three examples. One example is negative differential resistance devices, molecular rectifiers. Rectifier is the molecular jargon for diode, and photoconductive switches. So I will show you examples of three devices. I will show you that on the molecular scale, the physics that dominate these devices are quite different than what you're used to in semiconductor systems. And there are a lot of puzzles. So this is roughly the outline of my talk. And let me start with negative differential resistance devices. I will give a very long and very detailed introduction, so you don't have to worry yet. But if you still want to learn more about the details, there is a recent review that Ben-Gurion Shu wrote together with me, and this has been published in JFIS Chem C quite recently, last year. And let me just remind you what a resistor is, although obviously this needs no introduction. You take some device, a metal wire, you put it under a bias voltage, and you measure the current, you're going to see something like this. Right? This is an ohmic contact, and the ratio between current and voltage is the resistance. Well, one of them is the resistance and the other is the conductance. I always get confused. So if you look at the conductance versus bias in an ohmic device, right? This is the derivative of the current with respect to voltage. It's just ohmic. It's a constant number. And this is the conductance of your device. And there's not much you can do with such a device. Right? It doesn't do anything. Therefore, it's extremely useless, and there's nothing you can do with it. Well, molecules behave quite differently, even at the level of resistance. And I will, of course, describe why this happens in a second. But roughly speaking, this is what happens when you connect a single molecule into your device. As a function of bias voltage, you will have something like this. Right? Very different than from an ohmic device. You get some very low conductance regime here. Then you hit something which looks like a resonance, and then things flatten out. And if you look at the derivative of the current versus voltage, this is the differential conductance, you see a resonance peak. And this is something like the density of states for transport in these devices, and this is what it looks like. So already these devices are very interesting, and you can think about things to do here. But in some devices, things go even worse than this. Some devices, if you apply a bias voltage, current goes up, and then it goes down. And this is already something very strange, because this means that something is happening to the molecule itself, to the system that you're probing. When you're applying a voltage, you're doing something to the system. And that something, in fact, reduces the current. Although, when you think of it, if you increase the voltage, you should increase the current, always, right? So if you take the derivative of the current with respect to bias voltage, what you will get is a peak, but then you will hit negative values because the slope, oops, sorry about that. Because the slope here is negative, so you get negative differential resistance. And this is something which you can actually use in microelectronics. And you can, for example, think about it. If you look at this example, and these are already examples for molecular junctions. So this is from the early 2000s, and this is not a single molecular junction, but this is a really something which has many, many, many molecules in it. So it's more like molecular electronics. And this is kind of what things look like. You apply a current, you apply a bias, the current goes up, but then at some point, clearly something is happening, right? And you get this drop in the current. And let's say your working voltage is somewhere around here, then you can see with very small changes in the voltage, you can make a very large difference in the current. And if you can do that, you can make an active device. And this is what people actually do. And you can measure the efficiency of negative differential resistance devices by the ratio between the current at the peak and at the valley. This is the peak to valley ratio. And here it's of the order of almost 10,000 or 1,000, something like that. So it's really big. It's a very nice device. This is an example for a real single molecule device from the group of Herr van der Zandt in Negev. And what they do is take this metal wire, they put it under a piezo, like a drawbridge, they break it like this, and then they sprinkle some molecules. Once in a while, a molecule falls into the bridge, and then they measure it. And you see current goes up, and then it goes down, and then it goes on. So this is very different physics than this. But this is in a real single molecule device. And there's a lot of theory going on about why this happens. And there are various explanations. Of course, I will not go through all of them. I will just give you the basic idea. And the basic idea is that negative differential resistance always involves changes in the molecular orbitals themselves. I will, of course, explain. So this is a crash course in transport through molecular devices. And molecular devices typically look like this. There are electrodes. These are these yellowish things, because typically electrons are made of gold. So I'm drawing them with yellow. So what is the main characterization of the electrodes is simply that they have a Fermi function for the electrons. And that Fermi function is defined by a single number, which is the Fermi level, and also the temperature, of course. But for our case, the temperature is the Fermi level is the main quantity to take into account. And we have the molecule in between. Now molecules are kind of like semiconducting quantum dots. They have a discrete set of energy levels where the electrons can occupy or not. So in the jargon of chemists, I've been in the chemistry department for 4 years now, so I can talk in the chemist jargon. This is called the highest occupied molecular orbital, or HOMO, and this is called the lowest unoccupied molecular orbital, or the LUMO. In the language of semiconductor, this is just the valence and the conduction states. So whatever language you want me to talk, I can do, it's fine. I speak both languages. But really what it is places where electrons can sit. But they can sit one at a time. So this is not a semiconducting bulk. It's a tiny semiconductor where it can occupy a single electron. That's why it's so interesting. Now let's consider just transport to one level, because it's all the same. They do not really talk to each other, although sometimes they do. So what happens? let's consider about this situation. Now you're at zero bias. Of course, no current is flowing. Now you increase the bias a little bit, but you're still outside, this level is still outside the bias window. So the probability of an electron to hop from this level to this electrode is still exponentially small. So there's not going to be much current going. The only place where things will make a difference is when this level, when the voltage bias is so low, that this level hits the valence level or the home, right? Because now it's very easy for an electron to hop from here to here, and once an electron hops, it will easily be filled from this electrode, so we'll start seeing some current. And of course, now you are within the Fermi window, so we'll get constant current. And of course, now, as long as you increase, nothing will happen. If you increase it even more, now you will start to see conduction also from this conductance level or the LUMO level, and you will see another step. So typically you should see two levels, but it's very hard to reach that because this distance is something, anything between 5 and 8 electron volts. So you're going to burn your device way before you reach that level. So typically this is what we see in molecular devices. Now, if you think about these longer molecules, and if you want to see negative differential resistance, you need to think about these longer molecules. So this is a toy model for a long molecule, just two levels, connected. Right? Think about this in terms of tight binding real space model. So you have two sides, they are connected with each other, and they are connected to these Fermi electrodes. Now, if I would use that same line of thought, this is what would happen. You open up the Fermi window, nothing will happen. But in real life, this is what happens. Because when you make a voltage, you're going to have an electric field inside the molecule, right? Inside your junction, it's just a capacitor. It's two electrodes and something in between. So you're going to have an electric field inside it. And that electric field will affect the orbitals themselves. So you're going to see a drop in the voltage or in the potential along the molecule itself. Now, as you increase the voltage, you increase this electric field, you're going to influence the orbitals more and more. Eventually, whatever gain you have from increasing that voltage is lost because you contorted the orbital structure so much that they are no longer conducting. And then the current will go down. And this is kind of the picture. And again, it's all detailed in various papers. And this is the picture. And what motivated me to go into this field was actually, this is the first story, the experiment by Ben-Gurion and his group, where they studied this molecule. It has a name, which I don't know because it's in chemistry, and honestly, we don't care. It has a ruthenium core, it has some nitrogen, some thiol group at the end, but there's nothing very special about this molecule. Trust me, not very interesting. I will show you much more interesting molecules in the next. But the thing is that these experiments done on this molecule were very strange because they do not follow the conventional ideas of negative differential resistance, which I just showed. What they see typically in these kind of experiments, so the way it's done is that they do this experiment many times. Now, when they open and close this drawbridge, every time the molecule sits very differently. So sometimes it's like this, and every time it does that, it's coupled differently to the electrons. And this coupling becomes very important. So what they typically see in these molecules, in the same setup, when they do these statistics, they see three families of curves. One family which has a very small conductance, these are the blue lines. One family which has a fairly large conductance, you see this is almost ohmic. And one family which is intermediate. And only in this intermediate family did they see this negative differential resistance. Now, if the argument that I said earlier is correct, then you should have seen this negative differential resistance in all the samples, because it's a property of the molecule and the surroundings. So it's very hard to explain these data with the standard theory of negative differential resistance. What other thing they can measure is they can couple force measurements to transport measurements, And what they see is right when you see this negative differential conductance curve, you also see an increase in the local coupling between the molecule and the electron. And it's quite robust, and it's quite statistically significant that there is a relation between these two. So these are the two clues that we have. So just to summarize, it has a low bias, relatively low bias negative differential resistance, rather weak, yes?
Can you say something about how they measure the force?
Well, I don't know the details specifically. Basically what they do is brake measurements. They open the gate piezoelectrically, and then they burn the junction. And they correlate and they can calibrate how hard it is to burn the junction with the amount of force extended on the molecule. Because when the molecule is weakly coupled, then it starts to vibrate and it detaches very easily. And when the molecule is strongly coupled, the vibrations are kind of pinned, are weaker, so it's harder to detach the molecule. This is roughly how they do it. But there are various ways to do it. And Ben-Gurion is one of the pioneers in measuring force. This is roughly, but the details are of course, are experimental details. They're too complicated for me. They are. Okay, I just have to say, these measurements are extremely hard. I mean, there are not many groups in the world who can do these kind of detailed single particle, single molecule measurements. Even these days, there are maybe 5 or 6 groups. So it's quite hard. So they see a small peak-to-valley ratio, right? Something like 1 or 2, but only at intermediate conductances, and it's correlated with the coupling strength. I'm just mentioning there's no hysteresis because for various reasons. But these are the two main ingredients. And thinking about this, we came up with a theory which is, of course, borrowed from a semiconductor theory. And the idea is very simple. So this is kind of a schematic of the molecular junction. Now it's very big. And the molecular junctions always look like this. You have, in real space, you have an electron, and it jumps into the molecular orbital, and then it jumps into the other side. Of course, it can go the other way around, but it's the same thing. And the idea is that when an electron jumps into the molecule, it leaves a hole behind in the metal. Now, if these things live long enough, they will interact with each other. They will form an exciton, just like in semiconductors. And this exciton binding will open another channel for transport. In other words, this will change things, because now, if the electron wants to hop to the other side, it has to overcome this binding energy, right? So in that sense, this electron feels like it's coupled much better to this side than it would if there would be no exciton binding. So really what happens is this, of course, I'm showing a bit of formulas, but trust me, if this makes you dizzy, it's perfectly fine. This is the standard theory of electrons in molecular junctions. You have electrodes which are just free electrons. You have a molecule which you can model with various things. Here I just take a single level, it's very, very simple. And you have molecule-electrode coupling, so just an electron jumping from the electrode to the molecule and jumping back. That's it, that's all there is to it. But in this system, we also add the interaction between the electrons here and the holes here. And that's all there is to this theory. And this has been considered in the past, but only in terms of studying the properties of the surface and not in the context of transport. So this is pretty much what I do. And I'm not going into the details, but you can do various mean field decompositions. And what you really get is a renormalization of the coupling. And this renormalization actually depends on this guy, and this guy is a fancy way of writing the current. So what you really get is something of exciton coupling, which depends on the current through the junction itself. And this has been, it's quite simple to excitonic coupling in bilayers. You can actually see this. I think in bilayer graphene, people have tried to see exciton binding. I don't know if they succeeded. It's found. So putting all these in the machinery that theorists have for calculating currents, we do that, and as a function of this exciton binding energy, you see that you develop a really nice negative differential resistance peak. So current goes up and then it goes down again. These are just the numerical parameters. And what I can also calculate is the coupling itself. If you want the force constant between the molecule and the electrode, and this is the calculation, and this is the experiment. So at least qualitative, we have a reasonable story. And the story is really that the origin of this rectification here is not to the change in the orbitals themselves, but due to the normalization of the molecular electrode coupling via interface exciton binding. So this is a nice story, and it captured the eye of Ben-Gurion, who invited me on, and of course you can play with, you can play with the parameters, put it with realistic parameters of what this binding energy is, and you can also explain why this only happens at intermediate couplings. Because at weak couplings, also presumably the coupling itself is the binding is also weak, and at very large couplings, the binding doesn't change much. So only at intermediate couplings you actually see this change over the background. So we can actually explain why this happens. So this caught the eye of Ben-Gurion, and he invited me to his lab, and out of this first visit came the story of molecular rectifiers, and what I will tell you about has been recently published in Nature Chemistry, and it's the world's smallest diode. It's made out of a single molecule. So it's a nice story, and the story goes like this. I went to Ben-Gurion's group, and he told me, Yoni, look at our really, really cool experiments. We get really large rectification. And I looked at this molecule, I looked at this data, which I will of course explain in a second, and my immediate answer was, something is wrong, this is very strange. Your molecule is perfectly symmetric. This was my first reaction. So let me first try to explain to you why you need asymmetry in order to get some rectification. So rectification is diodic behavior, and diode is just a valve. If you have a diode, the current can flow in one direction, but it cannot flow in the other direction. And of course, we use those all the time. There are billions of diodes in this device, because when you put two diodes together, one opposite to the other, you get a transistor, essentially. So if you can make diodes out of single molecules, that's really the first step into making, hopefully, transistors. So that's why we want to make diodes. And typically, this is what it looks like. So you've already seen this image. When you have current, when you have bias voltage, you kind of tune the properties of the molecule. In semiconductor language, this is like bending the vacuum level, right? So this would be the picture of a square barrier when you bend the vacuum level, so you get a Schottky barrier, something like this. But if you have an asymmetric junction, an asymmetric molecule, when you apply a positive or negative biases, you're going to twist the orbitals in a different way. And if you're twisting the orbitals in a different way, then the current that flows through them, since it has to go through the orbitals, will go in a different way. That's why you will have rectification. The current will flow differently because you twisted the orbitals in a different way. So if there's no asymmetry, there's no difference in real space, and it does not translate into differences in the voltages, and you will not have diodic behavior. So this was my first impression. And this is the experiment that Ben-Gurion is doing. He's taking this molecule. This is a very big molecule. This is a DNA strand, and it's made of 11 bases, and this is the sequence. Now let me tell you something about DNA. It's a complicated system. I mean, it's a protein. It has a phosphorus backbone and sugars and metal molecules in it, and carbons and phosphorus and God knows. It's a complicated system. But the good thing about DNA is that the biologist has been playing with it for 60 years. And trust me, they have become really good at playing with it. So essentially, if you want a specific basis, all you have to do is Google the basis and you'll get a protocol for getting it. Or if it's long enough or simple enough, you can just buy it on eBay or something like that. That's it. They really know how to make things with DNA. And this is why they want to do it, right? There's nothing special in terms of electronic properties with DNA. It's just the variability and the know-how is quite astounding. That's why we want to use it. So he ordered this molecule. This molecule looks almost